other activities to bring science to the mainstream and also bring science to the common people is one of the very important activities HN had in his mind. I remember during our college days, he had also started activities where bringing in radical thinking. I remember attending Abraham Coor's lecture as part of HN's activities of bringing in scientific temper and scientific thinking among students and the people in general. So thank you, Ramrao, for giving me this opportunity, and I feel extremely happy to be here. The program has in general space for national development, then space application, self-reliance in satellite technology, self-reliance in space transportation, working on low-cost access to space, then space science and interplanetary exploration, on international cooperation, then also certain technology developments which have been going on. In all this, the space program itself, we owe a deep debt to this one person, a worthy son of soil of Gujarat, Shri Vikram Sarabhai, who, when the first satellite was put in space by Russia, visualized how a new technology can be used for a country like India, for bringing in development, how a new technology can be made use of for fostering development in the country. So we still remember his saying where he repeats, there are some who question the relevance of space activities in a developing nation. He said, if we are to play a meaningful role nationally and in the Committee of Nations, we must be second to none in the application of advanced technologies to the real problems of man and society. True to this, ISRO has been striving all along to bring in the space technology for the benefit of India, and like Ramarao mentioned, today definitely the world recognizes ISRO because as an agency which has brought in space technology for the benefit of the Indian development. Give you some brief on how things happened. It got initiated in the 60s. 57 was the first Sputnik put in space. Then in 1960s with INCOSPAR the activity started, and the program itself has many facets. Its prime is the space application, and for doing this application, Earth observation activities, then satellite communication, navigation, space exploration, and to ensure that we are able to do all this, developing launch vehicles and the satellite and also the advanced space systems. To enable this in the country, three main subsystems were established: an INSAT coordination committee and under planning commission, National Natural Resource Management System, and then an advisory committee on space science to deal with the science activities. And the vision was harness space technology for national development. In attempting to address the issues of the country, some of the things that went behind the program. See, we have only about 2% of the world's geographical area, 4% of world's water resources, and of course 17% of world's population. And then it has very large diversity, socio-cultural diversity. We are a predominantly rain-fed agriculture. Then declining per capita availability of land and water, and then over-exploitation of groundwater. And we have about 170 districts which are multi-hazard prone. Towards addressing this, today we can see that ISRO has completed about 121 missions, out of which 73 satellites have been put into space, which cover remote sensing, communication, navigation and planetary exploration, and 46 launch vehicles covering satellite launch vehicle, augmented satellite launch vehicle, PSLV, GSLV, and the next generation Mark III. Apart from this, we also had the space capsule recovery experiment and the crew module, atmospheric re-entry module. And we have launched about 40 satellites for 19 countries. Now, if you look at some of the applications that have been done, the very first major experiment that was conducted by ISRO was what is called a satellite instructional television experiment, which, when it was done in 1975, happens to be the biggest experiment of this kind in social media. And for this, what was done is, we borrowed a satellite from America. The satellite was moved over to the Indian longitude, and in about 4,000 villages, equivalent of today's direct-to-home television systems was established. You can imagine in 75, if you are saying that in a village, you are setting up a direct communication receiving from the satellite broadcasting, the kind of difficulties that people would have faced. But then, it was this experiment which demonstrated to the country and also to the political bosses of this country the enormous power of space technology for improving the process of education and also for enabling the information dissemination to the entire country. Because during those days, probably some of you will remember, the television was available only in 4 cities and 4 metros, and in nowhere else you would be able to get any broadcasting. Starting with this experiment, the government got convinced that the space technology is definitely going to benefit the country in improving the standard of living. And with this particular experiment, both the program of Indian National Satellite Series and the Indian Remote Sensing Satellite Series got approved by the politicians simply because they saw in it the value of their ability to reach the entire country sitting at one place. Then the communication itself, starting with this site program, then we had an opportunity of using the Ariane passenger payload experiment. When Ariane launch vehicle was doing one of its trials, they gave an offer that if you want to put a satellite, we are ready to fly for you. Because of the risk involved, others were not ready. And ISRO, because it wanted to demonstrate and work on technology, immediately took up this opportunity and built one of the first 3-axis stabilized satellite. Because up to that point of time, the concept of stabilizing the satellites in orbit using only spinning was there. And both the INSAT series of satellites was going to be a 3-axis stabilized satellite. And then subsequent to that, we had the INSAT-1 series of satellite, which were procured as per our specification from Ford Aerospace. And subsequently from the INSAT-2 series onwards, the whole satellite, communication satellite, are being built in the country. And then we had the GSAT series, and currently we have GSAT 8, 12, 10, 7 and 16. They are all providing various application activities, whether it is mobile telephony or FAC, VSAT data connectivity, point-to-point communication. It was this satellite space-based communication which enabled in the 80s and 90s a large-scale availability of both broadcasting as well as telephone connectivity within the country. Today, of course, you have, in addition to the satellite-based connectivity, terrestrial connectivity based on fiber optics and other Wi-Fi and mobile communication through the terrestrial services. And while we started with Apple, which was one of the 3-axis stabilized satellites, then we went through the INSAT-1 series, 2 series, and today we are ready to launch in August, 25th of August this year, one of our GSAT-6 satellite, which is going to carry a very large size antenna, a 6-meter diameter unfurlable antenna, which is going to provide with very small handheld terminals connectivity for people, both for communication as well as for broadband connectivity. This will be available, of course, for strategic sector initially. So the development encompassed telecom speech circuits to start with, then broadcasting direct to home, then mobile satellite services, then we had the private and news gathering services, radio networking, and about 250 cyclone warning dissemination system across the country, and about 5,500 direct receive systems for enabling training and development communication, for telemedicine, tele-education, and also village resource center. And apart from that, a large number of meteorological data dissemination systems which provide the connectivity for both weather forecasting and weather monitoring activities. Today in telecom, we have more than 10,000 BSNL circuits, 1.7 lakh VSATs, and DTH itself more than 4.2 crore DTH subscribers, radio networking, and then we have work on tele-education and telemedicine being done. Apart from this communication activity, one of the major developments that have happened is we have brought in our own navigation capability using Indian Regional Navigation Satellite Series, which is going to be a constellation of 7 satellites. Right now we have 4 of them up in space and providing independent positioning capability using receivers which are built in the country. In addition to that, there is a scheme called the Gagan, which makes use of specific set of information transmitted from the satellite transponders, which enables GPS system to ensure what is called safety of life and assured integrity. And this service has been recognized and is declared operational by Director General of Civil Aviation, where over the Indian sector, this fills the gap for the global aircraft enabled with what is called an S-bus receiver. It enables the aircraft to make use of for this service for en route planning and also for precision landing in the airports. And this also has been made operational since April of this year, and work is in progress for ensuring that almost about 1,000 odd airport strips will be provided with pseudolights, and it will become suitable for even precision landing subsequently. Apart from communication, we have been working on Earth observation satellites, which provides a constellation of satellites encompassing natural resources studies, agricultural crop inventory, and I'll show some of the actual samples of these applications in subsequent slides. Then one of the activities that went on in a big way in the initial years was identifying the potential groundwater zones and potential fishing zones. You'll see some of the application slides subsequently. Here also, like in the communication series, we started way back in 75 with the Aryabhatta as the first satellite that was launched. Here also ISRO made use of all the available opportunity that when Russians offered, we will carry few of the satellites free of cost, we'll launch for you. We took up that opportunity, and in 79 and 81, Bhaskara 1 and 2 satellites, which were the forerunners for the remote sensing satellites which were subsequently built, they were configured with a television camera experiment, and then we learned the ropes for providing to the country information based on Earth observation system. And today we have about 13 operational satellites, both in the low Earth orbiting platform as well as in the geostationary platform, encompassing both visible and also microwave. Microwave sensor is also important because during the monsoon period of a significant portion, we have cloud cover which will not allow visible sensors to look at Earth from space. So we started this program with Bhaskara 1 and 2, which carried what is called a slow scan Vidicon camera at that time, and it was providing 1 kilometer spatial resolution images. These were the first images that we got from these camera systems. Then very soon we built our own remote sensing observation system, which was in 1995 when this particular satellite went up. It was designed for ensuring for the Indian agricultural system, providing a data set which with 5-day repeativity, it was going to provide information enabling the phenology study of the crops and also high resolution images up to 5 meters. on a single platform, conceiving that all such three imaging systems work together and provide data for our specific application was actually hailed world over, and India was also able to capture the international market for imaging data, remote sensing data. From 1995 to 1999, we had the distinction of providing to the globe higher spatial resolution imagery in the civilian sector. In the strategic sector, of course, there were much better resolution, but in the civilian sector, these imaging capabilities were actually the forerunners and provided leadership to the Indian programs. Then we also built what is called a Cartosat 1, which is an along track stereo system. This was launched in 2005, and this is one of the satellites with which we are able to generate for the entire country a digital elevation model, which provides the basis for generating both orthorectification and cartographic maps. And then today this is extensively used for a host of applications in the country, and even on our Bhuvan website we are able to provide orthorectified images. Today you have image data which is having an accuracy better than few meters for any point on the surface of the Indian landmass. Then we also built early in 2001 a better than 1 meter resolution imagery. In 2001 technology experiment satellite, and then Cartosat 2, then subsequently Cartosat 2A and 2B. These were realized, and they continue to provide high resolution imaging capability to us. Then another very important application which was developed, and again we were leaders in the global community, is what is called a prospective fishing zone identification using the instruments called Ocean Color on OceanSat series. From 1999 we have been providing, based on the thermal fronts and also the color images that you get from the satellite, what is called a potential fishing zone identification, which the data is disseminated to the fishermen in the country from 99 onwards, and this one act alone saves to the country more than about 20 to 30,000 crores per year, simply because the fishermen go to the place where they get an improved catch and they have to spend less fuel, both diesel and petrol, in doing that. And both the success rate has been evaluated, and NCAR in its publication has shown that this particular activity of Department of Space, which has enabled Ministry of Earth Sciences to set up a specific facility in Hyderabad called Indian National Center for Ocean Information System, which is providing. You are also familiar that India has a large coastline, almost 7,000 kilometers, and this is one of the very important services ISRO is able to provide. Similarly, looking at the difficulties of getting images of Earth from space in the visible and infrared region because of the cloud cover, we also developed what is called a C-band synthetic aperture radar. This also was fully indigenously developed using the facilities within the country. We enabled the Indian industry to build the transmit-receive modules and also phased array antenna system, active array antenna system, which provides better than 1 meter resolution and also up to 50 meter resolution. And this can give you, through the clouds, images of Earth, and it has got a large amount of applications. This is one of the images which shows to you how an optical image looks at the snow and how a radar image is able to see below the snow cover the glacial lakes also it can see. Another important activity which ISRO has been able to successfully transfer in terms of technology to a user ministry is what is called a FUSL program, wherein for a number of crop types, today the Mahalanobis Center for National Crop Forecasting in Delhi, which has been established 3 years back, is providing to the Government of India a forecast which is 3 months ahead of crop forecast, crop harvesting, 3 months, 2 months and 1 month in advance. What is the likely yield of rice, wheat, rapeseed, mustard, sugarcane, cotton and jute? So these technologies have been developed and transferred to the user ministries by Department of Space. And then another thing is in terms of in Karnataka itself, it demonstrated the efficacy of space-based information system in a project called Sujala, which also won international, both World Bank and other acclaim, because it involved the users, and to the users the information was taken, and then through their help the small watershed development, and then how preserving the water, rainwater, and conserving it, how it recharges the nearby wells, and through that how the vegetation improves. All that was demonstrated using experiments like this. Similarly, the satellite data is used for monitoring the irrigation benefit program. Today, the government of India and also many of the state governments make use of the satellite data for verifying whether the programs what they have taken up is actually giving yield or is producing the desired results or not. And also when some large canals etc. are constructed, at some places you can clearly see that most of the work is done, but at some places the work is not completed. This can easily be picked up both with the high resolution images and other images which are generated from the satellites. Then groundwater potential mapping. This was one of the very important activities in the 80s and the 90s, where the bore wells which were being done earlier, drilled, were providing less than 50% success rate. The success rate of bore well drilling went up to 90 to 95% with the kind of satellite-based data and also the in-situ data that was used for providing information to the community. Then also reconciliation and general centralized GIS database for net file, forest, and then forest encroachment and monitoring. Also the data is extremely useful. And then urban sprawl development in Bangalore itself from 1965 to 2014, if you see how progressively the number of lakes are reducing, is all captured by these images and they are available. Then another interesting activity that has been taken up recently as part of Department of Culture is with respect to the heritage sites, generating a database where at each heritage site you have to demarcate protected zone and then no development zone, demarcations have to be done. Using the satellite data, these activities have been taken up, and in Karnataka almost about 258 heritage sites, this work is done. And then we also have a program where we want to involve school and college students for facilitating some in-situ observations at these locations and then providing the database to the regional center, archaeological centers, and who will use this information for their planning. Apart from the low Earth orbiting satellite technology, we also did right from INSAT 1 year onwards the imaging from geostationary platform, which was one of the very essential requirements to ensure the impact of cyclone is not felt in terms of at least loss of human life. Many of you will be aware in the 10 years back or 15 years back, if you had a big cyclone, we used to have almost 20,000, 10,000 deaths because of that. But today, thanks to the data that is available from these geostationary platform imaging sensors, we get images every half an hour, and based on these data, you are able to actually forecast the landfall within half an hour and 20-kilometer error zone. And as a result of that, the disaster rehabilitation ministry is able to take corrective actions and evacuate people and ensure that last few cyclones we had hardly any deaths reported. We had built a VHRR, and then currently INSAT 3D, the third generation imaging system, which provides in 6-channel imaging capability, gives you every half an hour image, and also it provides you both humidity and temperature in terms of vertical temperature profiles. And we also have a number of microwave sensors carried on OceanSat, Megatropics, and also on Saran Arctica, where we have worked with international partners and providing, for example, in OceanSat 2 we had what is called an ocean wind vector information generation, which was being provided to the global weather forecasting community within 180 minutes of data acquisition. Ocean wind vector is an extremely important input for weather forecasting and weather modeling activities. So today we have, again, this is another success story where based on the data received from the INSAT 3D, through the India Meteorological Department, we are providing almost about 28 products which are being assimilated both in the numerical weather models of NCM, RWF and IMD, and the improvement in the near-term forecast of the India is greatly from these data inputs which are coming from INSAT satellites. Another thing is that, like I said, cyclone, we get a large number of images, and based on these, both the wind vectors as well as the high resolution images. Here you can see one of the image, why we call it as an eye of a cyclone, probably one of the ocean color imager, which shows very clearly that a cyclone has an eye. This just gives you an animation of how the cyclone track is predicted and also the landfall is predicted, and this activity is also based on the work that is carried out by Department of Space, and then this also is made available to IMD for their regular activities. And we also provide large amount of such information on our website called Meteorology and Oceanographic Satellite Data Archival Center. Here, not only the data from our satellites, but also satellites from the global community, which is relevant for weather monitoring, and also archive data of large amount of previous satellite data sets are available in this, and this is being progressively used by more and more researchers in understanding both the changes that are happening, because the data is available practically for more than 3 decades now. Similarly, we have a website called Bhuvan, which is in a way very different from Google, because while Google gives you the images of some of the latest images of the Earth, this Bhuvan provides you almost about 30 to 40 different thematic information layers, and today this is being extensively used for a large number of activities. Like we make use of mobile applications like called crowdsourcing, which is used to give you an example, during the Uttarakhand disaster, a set of teachers and students were trained for a week's time, and they went to the disaster sites, and about 10,000 locations, they were able to report what happened as a result of that disaster within a week's time, and this was used by the disaster relief commissions in planning the disaster relief activity. Similarly, in Andhra Pradesh, there is a dwelling, about 4 million dwellings being constructed by the Andhra Pradesh Housing Board, and out of that, again using this mobile app and the Bhuvan, the data on about 3 million dwellings have been collected and is made available to the department for both monitoring and planning activity. Today, this particular website is catching up, and we are able to provide large number of services to the citizens based on this. Then we also work for some specific areas like Northeastern region. We have a specific application, Northeastern region specific Space Application Center, which is set up. One of the ex-directors is here, they have done extensive work in these areas, in remote places and also difficult to work places, for bringing the space technology, for ensuring that the decision makers have the necessary inputs for carrying out their planning activities, whether it is disaster risk reduction or early flood warning or enabling tele-education and telemedicine activities. For doing all this, we had to build in self-reliance in satellites. We started with a small 400 kg satellite, and today we are building up to 4-ton class in GSAT-6, which I said is going to be one of the very advanced satellites with a very large 6-meter diameter unfurlable antenna, and in between we have the satellites which are having various capabilities in terms of technology. We started with what is called 3-axis stabilized platforms, or spin stabilized platforms, 3-axis, then highly agile satellite technology was developed, and then in terms of detector technology, starting from vacuum tubes, we are making use of solid state devices, and today in the country we are also building our own devices, including charge coupled devices in the Semiconductors Laboratory, Chandigarh. I am happy to inform you that just last month we had the first set of complete wafer process with the facility, 180 nanometer technology facility established in the country, and we have about 28 products designed in the country by the Department of Space, which has come out as full-fledged integrated circuits, and this is also a very good development. And we have been developing various technologies. This is one of the latest satellites which is currently getting ready for launch on August 25th. This shows about a 6-meter diameter antenna which is actually stored at the time of launch in the satellite, and after it goes to space it is unfurled. Today we have about 13 satellites catering to land and water, high resolution, then ocean observation, and also weather and climate. Then coming to the space transportation system, we started our work way back in '63 in sounding rockets, and initial sounding rockets were built actually based on what is called a knockdown kits. We had the privilege of working with French agencies which provided these sounding rocket systems. It was brought from France and assembled in Turles, Tumba, and then from that day to today, when we launched our Mars mission, the entire component on this Mars mission was fully realized in the country. That means between 1963 to 2013, we had developed from the satellite launch vehicle, which started with about 320 tons, about 100 kg satellites. Today we have about 2.2 ton capacity, and by the end of next year, we expect to reach 4-ton capacity using the GSLV Mark III. And as you can visualize, this requires a large amount of technology development and also a large amount of studies which are required, whether it is in basic studies in propellant, propulsion avionics, or strap-on technology, the guidance system, inertial guidance system, and also working on cryogenics. And as you can also visualize, these are areas where you will get very little information from others because of the dual nature of the technology. But all this has been mastered, and today we have 2 launch sites in Sriharikota which are used for launching our own satellite. Not only our own, but also we are able to provide launch capability to others. And on 10th of July, we are launching 5 of the UK Surrey satellites on a commercial basis. And in this, we have a large amount of technology elements for navigation, inertial navigation system, digital autopilot, then liquid propulsion system, solid propulsion system, and aerostructural things and aerospace mechanisms, mission design and synthesis. And you'll also be very happy to know that we realize 80% of the PSLV thing in the Indian industry participation. And we carry out the final system integration and assembly and testing at the launch pad. But otherwise, this is the kind of distribution from raw materials to fabrication of using large firms. We have about 80% of the activity done in the Indian industry. And large amount of subsystem, whether it's a liquid engine or even N2O4 plant, which is required as a fuel for this. Cryos, actually the motor casing for which maraging steel was required, that is also realized in the country. And titanium, a large amount of materials also are realized in the country. This again, very, very proud to tell that cryogenic engine GSLV Mark III, which is started from scratch, while up to Mark II, we had some interaction with Russians. This Mark III cryogenic engine is a totally indigenous development, and we are going through the phase of development, and we have completed what is called, you can see this engine, we tested for 635 seconds full duration, and it has worked extremely well. And we also did recently automatic mixture ratio control operation for 200 seconds, and a series of trials which gives us great confidence that our GSLV Mark III, which we are planning to launch in next December, we will be able to successfully put about 4-ton class satellites into space. And we have a large number. In fact, S200 solid motor is also indigenously realized, and this is one of the largest solid motors in the world, second largest. And we had just 2 weeks back a successful test which demonstrated the modifications we had incorporated in this particular system based on the trials we had carried out in December. Then GSLV Mark III, we also had an experimental crew atmospheric re-entry mission, which carried a module which can house 2 people, and this was taken up to a height of 100 kilometers, and it was released from space and it entered the atmosphere at about Mach number 5, and then it survived the atmospheric re-entry phase, and then it was captured and it's available at Trivandrum, and the entire insulating material which has been realized in-house has come out unscathed, and it has demonstrated the successful realization. And we also had, like I said, on the 28th of April, we had a full 600-second duration test, and last week about 200-second test we have conducted, and this is the example of the static test that was done on the improvised S200 motor. We are also working on, while we are doing the current generation of launch vehicles, we are also working on possible future reusable launch vehicle. We should reduce the cost of launching per kg from current rates to roughly 1/10 of it in the future. So the first of the experiments, what is called X1, is being attempted sometime in September, and we are getting ready, and a wing body system which has undergone a large amount of wind tunnel test and demonstration of its design efficacy. We were waiting for this trial to be done sometime in September this year, and then this will be the forerunner of a series of tests which will ensure that we will master over a period of time reusable launch vehicle technology. And in building all this, we have a large number of infrastructure which is required to be developed, whether it is a hypersonic wind tunnel test facility. Another thing you need to notice is large number of these test facilities are all indigenously designed and realized using the Indian industry to a great extent. And here one of the things you are seeing is also a plasma wind tunnel facility and a multi-object tracking radar. This multi-object tracking radar has the capability to see an object which is just 0.5 meters square at a distance of 1,000 kilometers range. And then this is another system which has been indigenously realized in probably 1/10 of the cost of what it is available from international market. And this is also realized using the Indian industry. Both the RISAT satellite and this makes use of the phased array and microwave systems, and the scanning, electronic scanning is done using the software program, and a large number of transmit receive modules which run into thousands are used in this. We also built a number of capabilities like a lithium-ion battery, titanium sponge, then wind profiler, which is required for us to study the wind conditions prior to launch, because sometimes depending on the wind profile at a height, we have to decide whether we can launch or we need to postpone the launch. So we have built a wind profiler at Sriharikota, which can give us up to 100 kilometers the capability to study both vertical and horizontal wind profilers. We also work on a number of ground systems to provide the in-situ observations for validating the information generated from the satellites, whether it is a LIDAR, this is done at NARL Gadarki, then sounding rockets. We also have ground telescopes, which one of them I'll show you subsequently in Udaipur Solar Observatory, and also we have the MST radar facility. And then again, compact antenna test facility and a large thermovac chamber vibration facility. And this is the multi-application solar telescope which has recently been installed in Udaipur, and this gives the capability to look at sun and some of the studies of the sun. This is some of the images taken from the Udaipur Solar Observatory. And we also work on a large number of indigenization of materials. As you can visualize, that there are certain things which, though it will be available, they will be available at an extremely high cost. More than the cost, you can always be denied these critical components. And if these critical components are denied, your program can come to a grinding halt. So to avoid such a thing, it's essential to identify a set of material which is required to be realized, and titanium sponge which has been realized. I am also very happy to report to you, we have been able to successfully realize tanks which hold the propellants in this, and we have been able to achieve more than 700 bar burst pressure. While the design was for 680 bar, our test showed up to 700 bar it survives, And previously we had to import this material, now we are able to do it in-house, and a large number of similar substitutes have been developed in the country using the facilities both within ISRO and also using some of the facilities across the industry. And looking at, in addition to the space science and interplanetary exploration, we started the work using some gamma ray detectors and radiation potential analyzer on SLOT satellite. Then X-ray astronomy payload was there on the IRS-P3 satellite. Then solar X-ray spectrometer and also the GSAT-2 satellite it carried. Then of course we had the Chandrayaan-1 and Mars. We will see some more details of this. And Lunar Mission, this was the first of our planetary, the first of our outside, you can say immediately the Earth's vicinity. While the Lunar Mission we did in 2008, it was very successful because this is the satellite which is credited with discovery of water on the moon. Though before that, a large number of satellites had made observation and even man had landed on the moon. The specific information of the processes that take place on the lunar surface and the proof of both hydroxyl and water molecules being present was actually demonstrated by this mission. And this mission also was an excellent example of our ability to work with international people, and in this launch we provided the opportunity for 6 international payloads, and then we had our own set of payloads, and we also built as a part of this system a 32-meter antenna in Bangalore in the Bailadu space, and this antenna also was completely indigenously realized using the industries in Pune and Bombay and Hyderabad and a set of Bangalore companies. And this carried a moon mineralogy mapper and a mini SAR from USA, and also it carried a smart infrared spectrometer, then miniature synthetic aperture radar, radiation dose monitor, high energy spectrometer, and it was covering from radio frequency right up to gamma rays. It had the observation capability. And then of course our Mars mission itself on the November 5th when this was launched. Actually many countries were not believing that India is going to have a Mars program which is going to take off. When on the 5th of November it was launched, in fact they grudgingly accepted, okay, a mission could be thought of and realized in a short time. And on the 24th of September 2014, when it was actually inserted into the Mars orbit, that is when people really took notice of the capability of Indian space program. And on the day of the insertion, many of the students, how much they were excited. On that day, as the insertion was happening, they were gathered outside their school and they were celebrating the event. And here also we had 5 payloads, all the 5 payloads built within the country for generating cameras, methane observation, mass spectrometer, and also Raman photometer and a thermal infrared spectrometer. Some of the key capabilities which were demonstrated in this is, as you can visualize, this is for the first time we were taking any object outside the sphere of influence of Earth. That means it was the first time experience for us. It was first time an object was going to go as far away as 400 million kilometers from Earth. And then we also had to make sure that this particular satellite, the propulsion system was required to restart after a gap of 300 days. Then we need to make sure that satellite carries enough autonomy within the satellite, because in this particular program we were going to have periods as large as 2 weeks where there will be absolutely no communication between the satellite and the ground. I am also extremely happy to report to you, just a few days back we came out of such a phase where Sun, Earth and Mars were in the same line, and we had almost for about 10 days no communication between the satellite and the ground station, and now we are receiving regularly the data from the satellite. Very soon we are going to resume all the operations, payload operations, and we still have a large amount of fuel available on this satellite, and we expect it to survive for quite a few years. And this demonstrated the capability of precise Mars orbit determination, and also the ability to conceive of an autonomous system in the hardware, and also the programmability on the satellite. And this is credited with top 25 inventions of 2014 Times USA. Then the Space Pioneer Award it won, and also it won the Indira Gandhi Peace Prize. So the fourth space agency and the first Asian country to successfully reach Mars. And of course, they are all extremely proud of this achievement. And these are some examples of some of the images that are taken from the camera itself. And then very soon we are also going to have an Astrocyte mission, which is again a unique instrument, unique platform, because it is going to carry X-ray, ultraviolet, and also visible and soft X-ray telescopes. And in a single platform from UV to X-ray, it will be able to study stars and galaxies. And we also expect to provide a significant amount of opportunities of observation to the scientific community of students and scientists in the country and internationally. And the satellite is right now going through the environmental test, and it is getting ready for launch in September this year. And Chandrayaan-2, of course, this will be our second mission to Mars. It will carry the soft landing capability. We are building a capability of landing using throttleable engines. Development is in progress, and the satellite will also be the lander will carry a rover which will go on the surface of Moon, and will collect some information, specific information, and enable in situ observation. While we do all this, we also have a large number of international cooperation and collaborative work where we have provided opportunity using our launch vehicles, our satellites, and our own launcher to payloads which are realized by other space agencies. One of the things all space agencies are realizing progressively is for societal benefit activities across the globe, the amount of money that is available from the governments to the agency is progressively reducing. So the space agencies have to work together necessarily to maximize the resources available with them. And it is in this context that more and more collaboration takes place between space agencies. We have worked with KNS for providing opportunities for certain microwave instruments to be flown, and this has also benefited us because we are making use of these microwave sounding instrument data in our own weather forecasting activity. Today it provides for on a timely basis for both NCMRWF and our IMD very useful input for weather forecasting activity. Then we have make use of telemetry and telecommand networks for a number of ground stations across the globe. We are also part of a disaster management constellation where we provide data to the countries where some disaster event occurs, and we also receive from other countries data during disaster events. Then we have a capacity building activity at Center for Space Science Technology Education for Asia Pacific, where the up to MTech courses are conducted for people from the developing countries in the region of Asia Pacific. More than about 1,500 people have been trained in remote sensing, geospatial technologies, communication technologies, and also navigation techniques. And we also work with various international space agencies like Committee on Earth Observation Satellites or Coordination Group of Meteorological Satellites, etc. We also have cooperative arrangements with a number of countries. And then working with neighbors, we are also developing a satellite for SAARC region, where we expect to provide to all the 7 neighbors a capability using the satellite communication information for on meteorology, disaster monitoring, and also their own telemedicine, tele-education activity can be supported. And we also provide under UNSCAP activities where for Sri Lanka we are doing some work, and there is also SAARC Strong activity where in situ observations systems are established, and through satellite connectivity information is brought in for use for various applications. Currently we are also working with NASA on a program called NISR, which is again an extremely important mission because this is a technology which is going to be actually put into practice for the first time, and a large antenna is almost about 12-meter diameter antenna is going to be used here, and using what is called a sweep sort technique, the data will be collected in the microwave region, which will enable measurement of Earth surface information, soil moisture, and also biomass estimation, and both for flood and oil slick, and it's extremely important for us. This is expected to be launched sometime in 2021. Then again, just to give you in all this, we also work on a large number of technology development to ensure that we have a large sound base in this area in terms of chemicals, in terms of propulsion system, navigation guidance, and also energy storage, spacecraft thermal control, precision engineering. This gives you just some more examples of such things. We are also working on docking experiments and also moon lander, ceramic matrix components, and then shape memory alloys, and a large amount of multi-walled carbon nanotube activities, and then quantum dot solar cell, and also fuel cells, nanofluid, and like I said, in semiconductor laboratory we have a technology development. We also have a commercial arm which is Antriksh, and which provides these services like whether it's remote sensing data services, communication satellites or satellite components, launch services, ground system and other services. We also provide some consultancy and training, and so far a large amount of launch vehicles have been used for providing satellite launch capability. And we also have a program called Respond, where educational institutions are given an opportunity to work on programs of our interest. More than about 1,800 projects have been sponsored with an amount over 180 crores, and currently about 87 new projects have been approved, and this is also a program which is continuing, and we make use of this program for providing support to conference seminars and also for universities and institutions. We have a set of specific cells at IITs, IISc and certain universities. In the immediate future, till March next year, this is our target. We have almost about 7 launches. First one is on the 10th of July. We have the disaster monitoring constellation, 3 satellites of UK plus 2 more small satellites being launched. Then GSAT-6 going on our own GSLV Mark II with a indigenous cryo engine on 25th of August. Then in September we have the Astrocyte. Then in September we will also have the reusable launch vehicle technology demonstrator. Then GSAT-15, which is a large capacity communication satellite which will be launched by Ariane in October. Then we have another commercial launch for Helios on PSLV. Following that, we will have 3 of our satellites of IRNSS series, which will be launched using again PSLV. And then following that, we will have GSAT-18 a procured launch. So we have a busy schedule lined up for the immediate future. That, in a nutshell, you can say is a glimpse of the various activities we have been doing. And of course, in a period like this, it's difficult to do full justice to all the activities we are doing. But at the same time, I think it should give a reasonable flavor of the various activities that we are doing. And in all this, one major thing you would see the underlying is how we can build the technology capability to specifically address the various issues that are affecting our country. Currently, we are working with the current government for almost about 65 to 70 departments, how each of the department can make use of space technology based tools in performing their duties, whether it is monitoring, planning, or in terms of dissemination of information or decision making. So currently a series of activities going on with all the central government and state government department, and the current government is extremely active in this, primarily because our current Prime Minister had the first-hand experience of using the space technology in Gujarat, and he had made extensive use of both the communication as well as remote sensing and geospatial technologies in planning the development in Gujarat. and he is the driving force for the current central government ministry, and he is asking them to look at how space technology can be used. As you can see, with our own effort over a period of 3 decades, maybe we were successful in about 15 to 20 departments effectively using the space technology. Very soon, this number is going to increase significantly, though it puts a lot of responsibility on Department of Space, but I am sure every one of the people in the Department of Space will be more than happy to contribute because it is for the benefit of the country. Thank you very much for your attention.